Swayam Prabha. Digital India. Educated India.
I hope all of you somewhat understand the unit 3 consists of probability distribution, Bayes theorem, Gaussian distribution, optimization, gradient descent and then Lagrange's multiplier. So, these topics you have to discuss related to some other books, and also you have to see the history of these ideas. So, further you have to read the details of matrix differential along with a short review of the required linear algebra can be found in Magnus and Neudecker of the year 2007. Automatic differentiation has had a long history, and we refer to Grivank and Walter the year 2003. Grivank and Walter in the year of 2008, and Eloit 2009 and the reference therein. So, in machine learning and other discipline, we often need to compute the expectation. We need to solve the integral of the form Ex of f of x equal to integral f of x into p of x dx. Even if p of x is a convenient form, example the Gaussian, this integral generally cannot be solved analytically. Therefore, we need a Taylor series expansion of f is required. So, we are often interested in summarizing sets of random variable and comparing pairs of random variable. A statistics of the random variable is a deterministic function of that random variable. So, the summary statistics of a distribution provide one useful view of how a random variable behaves, and the name suggests provide a number that summarize and characterize the distribution. So, we describe the mean and variance, two well known summary statistics, then we discuss two ways to compare a pair of random variable. First, how to say that the two random variables are independent, and second, how to compute the inner product between them. So, this unit is rather terse at times. Grinstead and Snell, the Walpole et al. Provide a more relaxed representation that are suitable for self-study. So, the reader interested in more philosophical aspects of the probability should consider hacking, whereas an approach that is more related to software engineering is presented by Downey. An overview of the exponential families can be found in Barnardov Nielsen's. We will see more about how to use probability distribution to model machine learning task in this chapter, and ironically the recent surge in interest in neural networks has resulted in a broader appreciation of probabilistic models. For example, the idea of a normalization, the flows relies on change of variables for transforming random variables, and overview of methods for variational inference as applied to neural network is described in the chapter of the book by Goodfellow et al. In the year of 2016. So, we sidestepped a large part of difficulty to continue random variable by avoiding measure theoretic questions and by assuming without construction that we have real numbers and ways of defining set of real number as well as their appropriate frequency of occurrences. So, these details do matter. For example, in the specification of a conditional probability P of y over x for continuous random variables, Proshen and Presnell in the year of 1998. The lazy notation hides the fact that we want to specify x equal to x, which is a set of measure 0. Furthermore, we are interested in the probability density function y. A more precise notation would have to say expectation of f of y over sigma of x, where we take expectation over y of a test function, f conditioned on the sigma algebra of x. A more technical audience interested in the details of probability theory have many options like Janes, Mackey, Jacob and Proter, Grimmett and Wells. So, including some of very technical discussion by Shinov, Legman and Casella, Dudley, Bickel and Dodson, Schindler. So, these are all the references you have to do. An alternative way to approach a probability is to start with the concept of expectation and work backward to derive the necessary properties of probability space. As machine learning allow us to model a more intricate distribution on even every more complex types of data, a developer of probabilistic machine learning model would have to understand these more technical aspects. Machine learning text with probabilistic modeling focus include the books Mackey, Bishop, Rasmussen and Williams, Barber and Murphy. So, the continuous optimization is an active area of research and we do not try to provide a comprehensive account of recent advances for the optimization. So, this is it comes in the optimization. For a gradient descent perspective, there are two major weaknesses which each have their own set of literature. The first challenge is fact that gradient descent is a first order algorithm and does not use information about the curvature of the surface. When there are a long valley, the gradient points perpendicularly to the direction of interest. So, the idea of moment can be generalized to a general class of acceleration methods. Conjugate gradient method avoid the issues faced by gradient descent by taking previous direction into account. Second order methods such as Newton method use the Hessian to provide information about the curvature. Many of the choices for choosing step size and ideas like momentum arise by considering the curvature of the objective function. Go 2017 and Boto et al. Is 2018. Quasi-Newton methods such as LBFGS try to use cheaper computational methods to approximate the Hessian, and Nozidal and Wright 2006. Recently there has been interest in other metrics for computing descent directions resulting in approach such as mirror descent. Beck and Tabello in the year of 2003 and natural gradient of Toussaint in the year of 2012. You have to refer the gradient descent method. So, the second challenges is to handle non-differential function. So, gradient method are not well defined when there are kinks in the function. In these cases, subgradient methods can be used. SOAR in the 1985 for further information algorithm for optimizing non-differential function. We refer to the book by Betskes. There is a vast amount of literature on different approaches for numerically solving continuous optimization problems, including algorithm for constraint optimization problem. Good starting points to appreciate this literature are the books by Lundberger and Bonans et al. A recent survey of continuous optimization is provided by Bubek. So, in modern application of machine learning often mean that the size of the data sets prohibit the use of batch gradient descent, and hence stochastic gradient descent is the current workhorse of large scale machine learning methods. A recent survey of the literature include Hasan and Bolto et al. So, for duality and convex optimization, the book by Boyd and Vanderberg includes the lectures and slides online. A more mathematical treatment is provided by Betskes, and recent book by one of the key researchers in the area of optimization is Nestorov. The convex optimization is based upon the convex analysis, and the reader interested is in more foundation result about a convex function is referred to Rockefeller in the year of 1970. Hirat, Urruti and Lamarchal 2007 and Borvian and Lewis 2006. The Legendre Fensel transform are also covered in the aforementioned books on convex analysis, but a more beginner friendly presentation is available at Zia et al. So, the role of Legendre Fenchel transformation in the analysis of convex optimization algorithm is surveyed in Polyak. Now, we have activities. Number 1, consider the following bivariate distribution P of x comma y of 2 random variables x and y y to x or x to y. So, here row wise is y1, y2, y3, column wise x1, x2, x3, x4, x5, the data is given. Compute the marginal distribution P of x and P of y and the conditional distribution P of x by y equal to y1 and P of y by x equal to x3. So, second problem, consider a mixture of 2 Gaussian distribution illustrated, the figure 6.4, 0.4 n of 10 C2 1001 and 0.6 n of 00, 8.4 2 2 1.7. Compute the marginal distribution for each dimension. Subdivision B, compute the mean, mode and median for each marginal distribution. C, compute the mean and mode for 2-dimensional distribution. Next, third question. You have written a computer program that sometimes compiles and sometimes not. The code does not change. You decide to model the apparent stochasticity of success or this is no success, success with this failure, x of the compiler using the Bernoulli distribution parameter P of x by mu equal to mu power x of 1 minus mu whole power 1 minus x belongs to 0, 1 and choose a conjugate prior for Bernoulli likelihood and compute the posterior distribution P of mu by x1, x2 and so on xn. Next, fourth question, there are 2 bags. The first bag contains 4 mangoes and 2 apples. The second bag contains 4 mangoes and 4 apples. We also have the biased coin which shows heads with probability 0.6 and tails with probability 0.4. The coin shows heads with we pick a fruit at random from bag 1, otherwise we pick a fruit at random from bag 2. So, your friend flips the coin, you cannot see the result, picks a fruit at random from the corresponding bag and present you a mango. What is the probability that the mango was picked from bag 2 and using Bayes theorem? So, next we have to discuss the fifth problem. Consider the time series model x suffix t plus 1 equal to a into xt plus w, where w belongs to n of 0, q and y suffix t equal to c into xt plus v, where v is equal to n of 0, r, where w, v are IID Gaussian noise variable. Further assume p of x naught equal to n of mu naught, summation naught. Next, sixth problem. What is the form of p of x1, x2, xr? Justify your answer. You do not have to explicitly compute the joint distribution. Subdivision B, assume that p of x by xt by y1, y2, yt equal to n of mu t, summation t. Compute p of xt plus 1 by y1, y2, yt. Number 2, compute p of x t plus 1, yt plus 1 by y1, y2, yt. Third, at time t plus 1, we observe the value y suffix t plus 1 equal to y bar. Compute the conditional distribution p of x suffix t plus 1 by y1, y2 and so on, yt plus 1. Next, seventh one, manipulation of a Gaussian random variable. Consider a Gaussian random variable x is equivalent to n of x by mu x, summation x, where x in r power d. Further we have y equal to ax plus b plus w, where y in re, r power e, a in r power e cross d, b in r power e and w is equivalent to n of w over 0, q is independent Gaussian noise. Independent implies that x and w are independent random variable and q is a diagonal. Then number 1, write down the likelihood p of y by x. Number 2, distribution P of y equal to integral P of y by x into P of x dx is a Gaussian. Compute the mean mu x and the covariance summation y. Derive your result in detail. 3 or C, the random variable y is being transformed according to the measurement of mapping z equal to cy plus v, where z in r power f and c in r power f cross e, where v is equivalent to n of v over 0 comma r is a independent Gaussian noise. Write down P of z by y, compute P of z, the mean mu z and the covariance summation z, derive your result in detail. The fourth one, now a value y bar is measured, compute the posterior distribution P of x by y bar. So, hint is the posterior is also Gaussian. We need to determine only its mean and covariance matrix. Start by explicitly computing the joint Gaussian P of x comma y. This also requires us to compute the cross covariance of x comma y of x comma y and covariance of y comma x of y comma x, then apply the rules for Gaussian conditioning. So, we saw that 7 based on the manipulation of a Gaussian random variable. Next 8, consider the univariate function f of x equal to x cube plus 6x square minus 3x minus 5. Find the stationary point and indicate whether they are maximum or minimum or saddle points. Ninth question, consider the update equation for stochastic gradient descent using equation 7.15. Write down the update when we use the mini batch size of 1. Consider whether the following statements are true or false. Number 1, the intersection of any two convex set is convex. Number 2, the union of any two convex set is convex. Number 3, the difference of the convex set A from another convex set B is convex. Next 10th question, consider whether the following statements are true or false. So, the intersection of any two convex set is convex, the union of any two convex set is convex, the difference of convex set A from another convex set B is convex. So, next 11th question, consider whether the following statements are true or false. Number 1, the sum of any two convex function is convex, the difference of any two convex function is convex, the product of any two convex function is convex. So, the maximum of any two convex function is convex. 12th, express the following optimization problem as a standard linear program in matrix notation. Maximum of x in R square, where script that is summation belongs to capital R, then p power t x plus script summation subject to the constraint of script summation is greater than 0, where x naught is less than or equal to 0 and x 1 equal to less than or equal to 3. Next 13th problem, consider the linear programming illustrated in the figure 7.9 of minimum of x in R square of phi 3 transpose of x 1 x2 subject to 2 2 2 minus 4 minus 2 1 0 minus 1 0 1 x 1 s2 less than or equal to 33 8 5 minus 1 8. Here the figure is already given in the lectures that you have to see and derive the dual linear programming using Lagrange's duality. This is 14th question. Next 15th question, you have to consider the following convex optimization problem, minimum of W in R power D of 1 by 2 W transpose W subject to W transpose W greater than or equal to 1. Derive the Lagrange's dual by introduction by Lagrange's multiplier lambda. Next 16th question, consider the non-negative entropy of x in R power D, f of x equal to summation d equal to 1 to d xt log xt. And 17th question, derive the convex conjugate function f star of s by assuming that standard dot product. So, hints is take the gradient of an appropriate function, hint is take the gradient of an appropriate function and set the gradient to 0. Next 14th question, consider the function f of x equal to half into x transpose a x plus b transpose x plus c. where A is strictly positive definite, which means that it is invertible, derive the convex conjugate of f of x. So, hence is take the gradient of appropriate function and set the gradient to 0. Next, the 15th one, the hinge loss, which is the loss used by support vector emission, is given by L of alpha equal to maximum of 0 1 minus alpha. If we are interested in applying gradient method such as L, B, F, G, H and do not want to resort to subgradient method, we need to smooth the kink in the hinge loss, compute the convex conjugate of the hinge loss of L star of beta, where beta is a dual variable, add L2 proximal term and compute the conjugate of the resulting function L star of beta plus nu by 2 of beta square, where nu is a given hyper parameter. These are all the problems you have to make an attempt so that you can get the idea of both probability and optimization. Thank you one and all. Bye.